coming in the exam. So focus with me, please, for the session today. Pumps actually is classified into two main categories: dynamic pumps and displacement pump. These are the two main categories for this pump classification. Dynamic pump like centrifugal or axial, centrifugal maybe radial or mixed. The main shape or famous shape for centrifugal, this one, this shape. You see this shape? This shape. This is called volute. This is set name volute. Okay. This volute, all the time the inlet, it is from center of this volute. Okay, this center to the impeller. Sometimes it's called I diameter. Okay. This is the impeller actually. This is the impeller. This is the plates for the impeller. So the flow in all the time it is from the center here. The out, it according to the type of the bump, maybe vertical, maybe horizontal. It according to the type of the pump. This is a dynamic pump. Other type is axial. The different category is displacement pumps, and in displacement pumps we have different types. But these different types, it is under two board. One is reciprocating and one is rotary. For reciprocating, it's like piston pumps or diaphragm pumps. And rotary is like gear, like loop, like screw, like vane, all these types related for rotary pumps, but all under the type of the displacement pumps. Let's see some notes to define or advantage and disadvantage for the dynamic pumps and displacement pumps. I will start by the important notes asked in the exam, and then going to little importance one by one. But I start by the important information first. For important information, should be know which type it is give us high discharge or give us high head. For high discharge, it's give high discharge but low head. Okay, related to or compared to the other type. This is what it's mean. High discharge compared to other type. Low head compared to other type. So high discharge, low head, it for dynamic pumps. But for low discharge, high head, it's for displacement pumps. Okay, so this is one of the important note to define dynamic pump and displacement pumps. Second point, also in the highest importance point, we can say for priming. For dynamic pump, priming problem or need to make priming, this we can see in dynamic pumps only. But for displacement pumps, there is no priming process. What's priming? Priming definition also for priming is important. Priming, it's to fill the pump from the suction to the discharge, all filling by water before you start the operation, to be sure everything is totally liquid, okay, before you start operation. Otherwise, you're going to make some problems like cavitation, for example. So it is important to be sure all it is fully liquid from start suction to the discharge. This is priming. This for centrifugal pump, we see this problem, but in the other type for displacement, we don't see any problem related for that. For dynamic pumps, it's continuous flow. For displacement pumps, the regular design, it is fluctuation, pulsating flow. Okay, maybe we define we make advanced design to cover this problem. Like for piston pump, we can put the piston from exit right and left to be in this side. We have a discharge going into back to the other side. We have another discharge, so we reduce the fluctuation, but still this part specified for displacement or fluctuation. The other one is continuous flow. Normally, dynamic pumps, it's used for low viscous flow, like water, for example, low viscous flow. Okay, so it's normally we use this one for domestic application. But for displacement pumps, it's used for viscous flow, like oil and so on. So we use this one in industrial application. Other also classification between these two. For it's not importance, just little importance that. For dynamic bonds, it is low weight, less for less for less for what efficiency. Also cost. It's not expensive. Displacement pump, it is opposite for that. It's expensive, high efficient, used for it is heavy for weight, something like this. Okay. The file I sent you by WhatsApp, if you check now for the file, I give you this file for more information if you needed to read it. For bumps, this mainly for theoretical information. It gives you a review for all types, but the conclusion I give you the important notes. Just this for if you need to going to more reading. Just a minute, I open the file. This file I sent you already, my WhatsApp. I will share now this file with you. Let's see. Yes, this file here. You will see some pages at the beginning, just introduction content. Here talk about for centrifugal pump at the beginning here, and then going to positive displacement pumps. For each one we talk about for some information, basics, for some notes for each point. It's not a huge file. Total is around 40 page, but actually the first 12 page, it's not important, just to give you what we will do. Let's see, for example, this introduction for the first part for centrifugal, it's start at 12, page 12 here. So if you see here, this centrifugal pumps, this is a general shape for centrifugal. This is a volute here. This is volute, okay. And you see the mouse with, you see the mouse? This is volute, okay. And this is the impeller. This is actually the impeller here, okay. Sorry. This is the impeller. You see the impeller? You see the mouse or not?
Yes, I can see.
This volute. Here, start from there and take this shape. This all is a volute. Volute is the casing for the pump actually. This section all the time from the center, this discharge, maybe in this way, maybe it is horizontal. Impeller, impeller eye, this impeller eye. Let's continue. This type of the volute, single volute, double volute. Here is diffusers here in the pump inside. This is called diffusers, stationary diffusers. This is the rotating part for the impeller. Types of the impeller, we have single section, we have double section. This single section, this double section. This type of the impeller here, another classification which is open, semi-open, and closed impeller. Then going to the types for radial flow pumps. This radial flow, axial flow, mixed flow, multi-stage pumps. And the multi-stage pump, it set up to give us one important function. Multi-stage pump, it's coming to give us high head. To give us what? High head. Actually, it's by default centrifugal pumps give us high discharge. So we're going to use multi-stage pump if we need use centrifugal and we need high head. So it's give us high discharge by default and give high head by multi-stage pumps. This is, for example, the one of the side for this one for multi-stage pumps. This is a component. It's not important. If you need to read it, it's okay. If you need to pass, it's okay. The inside component for the pumps in details. What else? Okay, I can say it's not important. Going to the operation part. Operation, we will study here cavitation, and we know what's meaning of cavitation before, and how to avoid cavitation. And one of the important parameters to needed to calculate and convert for the pump data, it's called net positive suction head. We'll see this today. Yes, I think today at the end of the session. Yes, net positive suction head. This net positive suction head to tell us how to calculate this value, because this value it should be compared with the value given from the from manufacturer of the pump to check. According to this check, should be what you already calculated more than what you have in the pumps with manufacturer. In this case, it's okay. We already avoid cavitation, but if this not happen, so maybe cavitation it is happen in the process for the pump. So one of the important parameters should be calculated: net positive suction head, net positive suction head. So we have two things: net positive suction head available. This is what you already calculated by data for operation, and the net positive suction head required. Okay, this already should be not less than this value. From where this value? From manufacturer of the pump. Okay, so the available should be higher than the required. Net positive suction head calculation, it is consists from some parts, some items, some terms, but actually these terms for the exact calculation. For general definition, it's depend on two parameters. This also coming for theoretical exams. Okay, the two parameters here is pressure for the suction side, pressure for the suction side, and pressure for saturation. Okay, pressure for saturation. Sometimes we said this one is vapor pressure, vapor pressure. You have saturation pressure or vapor pressure, both the same meaning. Okay, so the difference between suction pressure and saturation pressure or vapor pressure, the difference between these two is give us net positive suction head available, net positive suction head available. Another note: net positive suction head available, it should be higher than or equal net positive suction head required. Also, the detailed equation for net positive suction head, it's important because it's coming for numerical. This part, what I said before, this is coming for theoretical. For numerical, should be going to describe the net positive suction head in details. So in details, you will see the four parameters included here for calculation by numerical, which is these two parameters. BA, which is referred to absolute pressure on the surface of the liquid. We see in detail this one during session, this absolute pressure, okay, on the surface of the liquid. BST, which is referred to B static, and this B static, it's calculated pressure due to the elevation between liquid surface and pump section. Actually, it's calculated from if this pump section here, so it's calculated, and this reservoir, we take it this flow from this reservoir. So the distance from the suction, this is a pipe suction pipe here to the pump. So the distance from the center line from the suction pipe here to the surface here, surface of the liquid here, this is called B static, okay, this B static, okay. But BA, it's absolute, which is referred to the pressure here, the pressure for this flow itself, okay. HF here, it's referred to head losses in the pump for suction piping. It means from suction piping, I start piping from here, this piping here for the suction, and the end here, this is the end pipe here for the suction. So the suction, we have this distance, which is some part is horizontal, some part is horizontal and vertical. We add both vertical and the horizontal, and we calculate the losses during this range all in the pipeline, okay, including fitting and everything minor losses. Also, we will see in details this one today. BS sat, which is referred to B saturation or B vapor. This B sat or B vapor, this vapor pressure or saturation pressure or vapor pressure of the liquid being pumped. And this one referred to the condition for saturation given according to the temperature and conditions for pump. We give you B saturation direct because this one mainly related to as a property, like for example this like property. Okay, so at a given temperature we can calculate B saturation. Okay, so it is related direct for the temperature. It's a property. Prevention for cavitation, uh, shut off head and bump run out. This shut off head, we see this one for maximum pressure at zero flow, and this maximum flow at minimum pressure we see. Then going to another part. What is another part? Positive displacement pump. Positive displacement pump. For positive displacement pump, also just to give us some simple notes for each part. First is the principle of operation, the concept for positive displacement, this reservoir, and what happened for suction stroke, discharge stroke, and what is the process phenomena for the positive displacement. Then going to reciprocating pumps here, and we see some different types like direct acting, indirect acting, just for reading. Okay, in exam it's not going in details for these items. Simplex, duplex, single acting and double acting pumps, power pumps. Then going to the other different categories like rotary pumps, like gear pump. We see also screw bumps, I think, loop bump also. What's loop bump? Screw bump. What else? A vein bump, diaphragm bump. Also, as you see, just a little half page, something like this. That's it. Okay. So this file is just supported for you for just quick reading and focus for the important notes. Let's go back for the original here presentation. The recording is okay. Yes, it's okay. Selection of bombs. Selection of bombs is depend on two things. What's these two things? Head and discharge. And the head we can see instead of head pressure. Pressure head is was the same. So if we know head or pressure, both the same actually. Head and pressure, and the other one is discharge. Capacity, discharge, flow rate, all the same also. Okay, according to these two parameters, we can going to make selection for the pump. We have two curved, one for pump curve and one for system curve, one by your calculation, one coming from the pump manufacturer, and the intersection between these two, it is a point of operation as you request. For series pumps, we will see that what happened for series pump. Series pump is the same flow rates coming, same Qn is equal Q out, but just we need to increase the pressure, and normally we use this type for centrifugal to obtain high head. For parallel pumps, it uses this one into almost to the same pressure head, to actually two pressure head the same. The main function for parallel pump is obtain high discharge, to obtain high discharge. So if we have single pump, we will see the curve like this. But if we have two parallel pumps, we will see the other curve is double this one. For example, if this one at flow y here, the value is, we will see this one at 2y, and then at the same pressure. So if we have flow at the beginning is x, so you'll see for two parallel pump is 2x double discharge at the same pressure. This parallel pumps. Let's see some theoretical questions for this part. This set of questions for theoretical to cover some important questions coming for pumps. Which of the following centrifugal pumps have higher specific speed than the others?
Axial flow.
Axial?
Yeah.
Axel.
Yes, exactly. Axial is have higher specific speed than mixed than radial. Pump transfers the mechanical energy of a motor or of an engine into of a fluid.
C. Pressure or kinetic.
Pressure,
Number C.
C.
pressure
Is the pre-
or
kinetic.
kinetic?
Yes, it's C.
Exactly, it is pressure or kinetic, actually, or both. So the correct answer is
D. D.
yes.
D.
Sometimes we have both.
C.
Which of the following is not? Be careful. Not type of positive displacement.
Centrifugal pump.
Centrifugal pump.
Let's see the correct answer.
Number C.
Volute bombs and vortex volute bombs.
Single stage, horizontal. C.
Single stage.
Vertical shaft.
It's actually single stage and horizontal also. What's volute? Can't see. See for which type?
Centrifugal.
Centrifugal pump.
Centrifugal bomb, exactly.
Yeah.
Which is the following
D.
example of
All.
rotating displacement?
All of them.
All of
All of them.
All.
what about
Yes. What pump is set velocity pump?
Centrifugal.
B.
Total displacement.
C. Centrifugal.
C. Centrifugal is a velocity pump. Yes. Discharge capacity of a reciprocating pump compared to centrifugal.
Lower than.
Higher than. Higher.
higher.
Lower.
Lower.
B.
Lower.
B.
Lower than, yes.
Yes.
Lower. Which pump is one suitable for application with very high pressure required?
Centrifugal pump. Sorry.
Centrifugal.
Reciprocating pump.
Reciprocating pump.
Reciprocating pump.
Yes.
Reciprocating?
Reciprocating.
Yes,
Reciprocating.
exactly. Reciprocating, correct. This one for the high pressure. What's the process of filling the liquid into the suction pipe and pumping it?
Priming.
Yeah,
Priming.
okay, this is important definition.
C.
What's 1 horsepower equal to?
75 hours.
734.
735 watts.
700.
735. D. 700.
Head developed by centrifugal pump depend on
Impeller diameter.
Impeller diameter and speed. E. Answer E.
E. Yes.
E.
both, yes? Yes. Multi-stage centrifugal pump used to obtain
High discharge.
Ah,
High
High
discharge.
head.
Yes.
High
A.
head.
High head and high distance.
I hit.
Head
Yeah,
at the
D.
start.
Head.
D. D.
Or D.
tricky questions. This. The exact answer is high head because it's
High
get
head.
by regular is default is give us high discharge. So multi-stage is give us high head. Centrifugal pump liquid enter from
Enter.
C.
center. Casing of centrifugal pump designed to
B, deviation.
B. Cavitation.
Loss of kinetic energy.
Loss of kinetic energy.
finish.
D.
D.
Have a debate between B and D, yes. Loss of kinetic energy. No problem, just a mirror between B and D. How to select pump?
Delivered flow and pressure.
Low under pressure.
Flow under pressure. Fluid coming into centrifugal pump is accelerated by
Impeller.
Impeller.
no.
Full failure.
B.
Centrifugal pump transferred fluid by converting
Mechanical energy to kinetic energy.
Kinetic to hydrodynamic. A.
C.
Mechanical to kinetic.
kinetic to the hydrodynamic. Kinetic to hydrodynamic. Centrifugal pumps are used to transport
Fluid.
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 fluid. Which among the following controls the flow rate?
Valve.
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 A.
Centrifugal pumps transfer energy from
Rotor to fluid.
Rotor to fluid.
fluid. Main function of centrifugal pumps. What?
Transfer pressure.
Transfer energy.
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 Transfer energy. Turbo machine work under
Second law.
First law.
second law. Newton's second law. Centrifugal pump is
Flow regulator.
A.
A. Turbo machinery.
turbo machinery. Primary selection tool is
Pump curve.
Pump curve.
yes. Which one is taken account during a characteristic curve?
Flow rate.
Flow rate.
Yes, excellent. What in the hydraulic head used to analysis?
Cavitation.
For NBSH?
Cavitation.
Yes, exactly. What's NBSH?
Net positive suction head. suction head.
Yes, excellent. This one is difference between
Suction pressure and vapor pressure.
Suction and suction.
exactly suction.
A.
What is the meaning of this form?
Net positive suction head.
B.
Net positive B.
Yes, exactly. Reciprocating
Positive
pump is
Positive displacement.
B.
positive displacement.
Positive.
Reciprocating pump classified according to
Number of cylinders.
number of
Drag
cylinders.
force.
Rotary pumps are commonly used to
Oils.
Lube oils.
lube oils. What is the form of BD?
Positive displacement.
Positive displacement.
Displacement. What's with the increase in the flow rate? What happened for efficiency?
Increases.
Decreases.
Same.
Increases. No? B.
Power output divided by power input is the efficiency. Output by input. For output, it is coming from the fluid, which is gamma QH pump. And power input is the electricity for power in. So what happened?
Efficiency increases because it's in.
Efficiency increases due to discharge increase. Difference in total head of the pump is
C.
Manometric head.
which one?
Manometric.
Is difference. So manometric. What is the unit of energy head? This one here is
Meter.
Meter.
still meter because he talk about for head. What's the meaning of this abbreviation?
Pump
A.
hydraulic efficiency.
Pump hydraulic efficiency. What this? What you said?
A.
A. Yes, excellent. With increasing power, what happened for efficiency?
Increases.
Which one?
Decreases.
Decrease.
Decreases. All agree? Yes. Let's start for numerical part. We will see some theoretical questions. It's not small questions. So make a relax, fresh, be ready for numerical part. Are you ready?
Yeah.
Okay. We studied before for the fluid mechanics in second session Bernoulli equation. You remember this? And you see Bernoulli equation classified in the head form by three terms: B over gamma plus Z plus V square over 2G is equal to constant. And with another name, H static plus H dynamic is equal to H total. Correct? Static dynamic equal to total.
Yes.
Great. Excellent. Should be steady, incompressible, and inviscid. But actually for energy equation, we're going to another things. Steady the same, incompressible the same, but we can working in the viscous flow. No problem for inviscid. Viscous flow. So it means viscous flow, at the beginning, velocity, it's not uniform. It's not like this. It's not like this. It's not uniform like this. But we can see velocity like this profile, velocity like this profile. So at the beginning, this velocity, it is referred to scalar value, which is something like this. So at the beginning for energy equation, it's not like this. So we're going to calculate average velocity. But actually in the numerical problems, we don't face for that. So the correction for the velocity or the V average is normally it's given as a V. So we cancel this, normally is 1, and V dash, it's the same V. Okay. Other parts for B over gamma and Z is the same. So what's different between energy now and Bernoulli equation? This, it is totally ideal case, but this one is including the other parameter we don't include here, like head of pump. So we can study pump inside the system. But for Bernoulli equation, we can study something passing through the pump. So no, I can't study, for example, from this side up to this side, for example, this area. So a long streamline like this, I can study between first point and second point. H total here is equal H total here. What happened for static and dynamic here? What happened for static and dynamic here? What is increase? What is decrease? No problem, but still H total is the same. But for energy equation, no, we have pump here, passing through pump. If passing through pump, Bernoulli, it's not allowed. Allowed is energy equation. So we can use it head of pump here in this equation. We can use it H turbine here in this equation. Also losses included. Loss included. Okay. But the other part, something like this part or this part is almost the same, the part for Bernoulli, not change. B over gamma plus z plus v square over 2g, but this at inlet or case 1, this at exit or state 2. That's it. Okay, this also considered as 1. So here, if we write it Bernoulli equation before during solving problems, b over gamma plus z plus v square over 2g for state 1 is equal b over gamma plus z plus v square over 2g at state 2. This Bernoulli, same like this part and this part, but adding this terms. So we talk about for energy equation. H losses, it we can see in the equation if the problem it is have losses. If no losses, we cancel this term. Turbine and the pump is according to the problem type. If the type you study of the problem is have a pump, so this we will see, but we don't see the turbine. If we see another application or another problem have a turbine, but we don't have pump, so we cancel the pump term and we will see the turbine term. Another point, why pump put it here in the left side and turbine and losses, it's put it here in the right side. This according to the function for each one. The function for the pump, it gives the flow energy. So I give the state 1 energy to obtain state 2. So energy for state 2, it is higher than energy for state 1 due to head of pump. So head of pump I added in this term because I add energy for the initial state. But other side for turbine, no. I release energy from first state to obtain electricity or something like this. So this energy I released, it is already including is the head of the turbine. So what's the remaining? This is the part for the remaining. So this part, it is less than this part due to H turbine obtain. Clear? Losses is the same also turbine. Losses, it means we lose some energy. So due to flow moving, the energy at start point, it is less than the energy for the end point. Due to what? Losses. So the difference between these two, it's get H losses. This is H losses. This is what is a reason for the energy is decreased from state 1 to state 2. It's going to H losses. It's not here because I don't add losses in the initial state. No, I obtain these losses due to the moving. So the losses plus the final state, it is obtain the first state. Okay. All this equation with all terms clear before I start for application for solving problems, because we're going to solve different problems types of ideas. So before you going to that, if you have any question for the equation itself. Also, don't forget happy face. Because happy face for Bernoulli, we'll see happy face together. For energy equation, we see happy face also. For this one not included, we will see also happy face. So happy face is one of the famous equation coming in the exam. Before going to next slide, start the numerical problems. Any equation for energy equation? No question for energy equation? Let's see. Okay. Read first one, please, and give me, and not give me answer. We solve it together, but just read it. I give you half minute to read it. Reading finish? Okay. Let's start solve. We have two different diameters between these two different cross sections area, A and B. One is 18 inch, one is 36. It's something like this. Something it give double diameter like this. So at this cross section A, the diameter for this one is 18 inch. The pressure for this one is 10 psi. The other section B, it is diameter have 36 inch, and the pressure is 10.9 psi. Determine the head losses between the two streams, 1 and 2. And he's give you the Q, the flow rate, 30 cubic feet per second. Let's start. Here to give the value for the losses, at the beginning we should write the equation for energy equation, B over gamma plus Z plus V square over 2G. This is state 1, this is state 2, so this is state 1. We have any bump? No. So we don't have bump, equal B over gamma plus Z plus V square over 2G at state 2 plus H losses, which is required, actually is required H losses, head losses. So going for one by one, here he tell you is horizontal pipe. So if this one is horizontal pipe, so the Z is the same level. So this Z is the same this Z, horizontal pipe. Okay, let's go for the next. Pressure. B for this value. Before we're going to continue solving, here as you see this psi, this inch, and this cubic feet per second. So the problem is better to solve it by what? It's better to solve it by
BS units.
British.
Yeah.
This is the easy way for that, correct?
Yeah.
So we will continue solving by British. Is better actually. So let's see. Continue by British.
So why is Z cancelled from both sides?
For Z,
Yeah.
Z horizontal pipe. So the level is
Same level.
same level, yes. So we have B, gamma, it's not given. I give you gamma here as a given here. 62.4 pound force per millimeter cube per feet cube, I think so, feet cube. So here pressure for section 10, so it's 10. BSI, it means pound per square inch, correct? Pound per square inch. So pound square inch is not matched with 62.4, which is have pound per feet cube. So need to change square inch to feet square, pound per feet square. So how to get it pound per feet square? This by multiply 144. 144. Please don't forget this number, please. Don't forget this number. Because inch to feet is 12. So from inch square to feet square is 144. Plus v square, you have velocity. This is another problem. We don't have velocity. So in the side calculation like this, we're going to side calculation here. We have Q, which is equal 30 cubic feet per second. So we can calculate velocity according to the equation AV. So V at 1 is equal Q divided by area 1. So this one is 30 cubic feet per second divided by pi over 4. D here is 18, which is equal to 1.5 feet, correct? Divided by 12. So 1.5 feet. Here,
Yes.
1.5 feet square. And you get V1. V2 is the same. It's equal to Q by area 2. So is equal to 30 cubic feet per second divided by pi over 4. 36, it means 3 feet, correct? So this one is 3 square. Get here the other one V2. So V square, V1 square. I get it here and I put it here square. 2 multiply G is 32.2. 32.2. In other side, B is 10.9 multiply 144 divided by 62.4 plus the calculation for the velocity also for V2 here, 2 multiply 32.2 plus H losses. That's it. Once you get the velocity V1 and V2, put it here and you can calculate the losses direct. So the exactly here we will see the big problem for calculation. For what? For calculation. To decrease the calculation, we have different options. Calculate direct this part first, like calculation like this. This calculation first, not white. I need black. Take this one finished, plus this one finished, and going to plus, then this one minus, this one minus. So we will get each losses direct. This way. Another way we can get it like this: 10 minus 10.9, 144 divided by 62.4. You understand me? I take this in another side here and take this 144 common factor and 62.4 common factor and only 10 minus 10.9 to decrease the calculation actually. Plus the same also 2 multiply 32.2 is common factor, and just I put here this V1 and this V2. That's it. All this is equal H losses, just to decrease the calculation as you wish. It depends for you in the calculator. If you are into going to stage by stage, going to first one. If you need to going to like this one stage, going to the second one. Okay.
Can you please explain again how gamma became 62.41? I'm sorry, I missed that part.
For what gamma?
Yes.
This gamma it should be given or save it. Two values I like to save it: gamma and G for British 32.2. These two values, please save it. Gamma and G. Let's see, use the value. Any other question for this? Hi, any other question? Okay. Then this 16.98. This 4.24. This one and this one. Okay, so let's go for the here and just put its answer here: 16.9 and 4.24. That's it. Okay. A check answer, please. You'll see the exact answer is 2.12. 2.12. Any question for this one? Any term not clear? From where, how to get it? All step clear?
Can you please explain the conversion of PSI to feet square? What is that?
This one, PSI
Yeah.
is equal 10. So I needed to change pound per square inch. This pound per square inch. So I needed pound per feet square. So I going to 10 multiply 144.
Okay. Okay.
Okay. going to multiply 144 to change it from feet square, from inch square to feet square, because as you know, from inch to feet divide by 12, so inch square to feet square 144. Okay, 12 is 144.
Okay.
Any more question? Okay, read first please. This here gamma, as you see, this is G. Let's start. Here, pump through water 50 from height from a reservoir where the water surface, increase this one here, elevation is 550. So this one is at elevation 520 feet, and go through and forces water through a pipe 5,000 feet long and 1 feet diameter. This pipe discharges the water into the reservoir when the water reservoir elevation, this elevation Z2 620. The flow rate is 7.8. This is the discharge, 7.85 cubic feet per second. Head losses in the pipe is calculated by this equation, 0.01 over dv square over t2g. Determines the head supplied by the pump. We need the HO pump, head pump. Let's see. Write the equation first. So the equation is P over gamma plus Z plus V square over 2G. This for state 1 plus H pump, because we have pump, is equal to P over gamma plus Z plus V square over 2G for state 2 plus H losses, because also it's given losses here, so we can going to calculate losses. Pressure, let's see. For this reservoir, it is atmospheric. Is what? Atmospheric. So this one atmospheric, and also this one for case 2 is atmospheric. So the pressure is the same, correct? This pressure is the same, this pressure. Both is atmospheric. This atmospheric. So it's cancelled together. Let's see the other one. Z. So for Z, this one is 520. This is the elevation for this one, and this elevated by 620.
Why we cancel this pressure, sir?
Again?
Why we cancel the pressure? Atmospheric? Can you
Same
tell me
pressure,
again?
same pressure.
I cancelled the two terms together. This one is atmospheric, open to atmospheric. So this one is atmospheric pressure.
Okay.
Atmospheric also.
Both side. Okay. Okay.
Both sides, yes.
Yeah.
Okay. So this 520 for Z1 here. Okay. But let's see the Z2. Z2 here is 620 feet. Velocity for here, this big reservoir. Normally for diameter large, very large reservoir, velocity all around 0, approximately neglect. Okay, so here for this velocity is approximately 0. Why? Because this big diameter, large reservoir, so we consider this as a 0. And the other velocity in state 2 here, also this open reservoir and huge. So this one is almost also 0. So both is cancelled. So what's remaining? Remaining is pump. So here is plus H pump. Other side is remaining H losses. Okay.
The water is flowing, no? Why velocity neglecting when water is flowing through tank?
Yeah, we have a velocity here inside the pipe because the diameter, we have diameter 1. So we can make a relation between the Q and the diameter and get velocity here, go through in the pipe. But for large reservoir, diameter is maximum. Diameter is big, very big. So the velocity is almost
The
zero.
surface or area of the tank, you mean to say?
Yes.
Okay.
So H pump here at the final, it is equal 620 minus 520 is 100 plus H losses. So the mainly unknown is H losses, which is given by this problem, this equation, sorry. So we can substitute for this equation. H losses, we can get it here. H losses equal 0.01. What's 0.01? We'll see later, as this one is friction factor. L over D, what is L? L is 5,000 feet, so feet is the same. Okay, no need to change something. Diameter is 1 feet. Good, feet is okay. Next, V square over 2G. We have velocity, it's not given direct. We have Q and we have diameter. So have here, we can in the side equation by Q equal AV. V is equal Q over A. So V is equal 7.85 divided by pi over 4, diameter, which is 1 feet square. So from this equation, we can get V, feet per second. So let's see this calculation after we finish the equation. 2G, 2 multiply G, 32.2, 32.2. Let's see this one, eraser. Thanks. Let's back to the this one. 32.2. From this one, we can get H losses, but after we get velocity first. So let's see the velocity. Velocity, 7.85 by 4 divided by 1. 9.99. This one is 9.99, which is almost 10. So we can write it here 10. And the given H losses here is around 78. This is what I remember because I solved it a lot. So this one is 100 plus 78, which is equal 178 feet. This feet. So this head by feet. Any question? Any question? Okay. Read first, please, this problem, and we're going to solve it together. Okay, ready? Let's go. This we have pump also. Okay. This section diameter here is 200 diameter, 200 millimeter. Delivers to the 150. So diameter here 150 millimeter. Velocity for this charge type is 2.5 meter per second. You tell me is two different velocities? For sure, different diameter, different velocity, continuity direct. At section E, pressure it is equal negative 40 kilopascal. At section B, the pressure is 410 kilopascal. The height between these two 2.5 meter. Required is power. Horsepower. Okay, horsepower. HP. Horsepower. And give you the power gamma QH. And give you not here, no friction losses. Okay, good. What's the equation used? B over gamma plus Z plus V square over 2G. Why are you going to calculate this one? Because we have here gamma QH. Q, we can get it easy. We have velocity, we have diameter, get it Q. Gamma, it's constant, which is gamma is equal rho G, which is equal 9810 Newton per meter cube. Okay, this gamma. Okay, coming from 1000 and 9.81. It tells me it is 62.4 for British, but this for SI unit because here millimeter and meter and so on. So what is the remaining H pump? So the way to calculate H pump, this way, B over gamma plus Z plus V square over 2G at state A plus H pump equal B over gamma plus Z plus V square over 2G at state B plus H losses. We have losses? No, so cancel. Let's start to substitute. B, pressure is negative 40 kilopascal, gamma plus Z. So Z, I put this datum. So Z here is equal to 0. And Z here is equal to 2.5. So this is 0. Velocity, I don't have this velocity, but I have this velocity. So by continuity equation, side calculation here, Q1 or QA equal QB. So A1 V1 equal A2 V2. What you need? V1. So V1 at cross section A equal A2 by A1 V2. So equal pi over 4 D2 square by pi over 4 D1 square V2. Pi over 4 cancel pi over 4. So the calculation here, D2 by D1 squared V2. So let's start to calculate it. I need to calculate. V2 is equal 2.5. D2 is equal 150. V1 is equal 200. So this one, it will be 150 by 200 squared multiply 2.5. What's value for this velocity? 150 divided 200 equal squared multiply 2.5. 1.4.
Sir, you need to convert mm to meter, right?
This millimeter, so it's no idea for to change unit here.
Okay.
It's both the same as like ratio. For ratios, it is not important. Okay, but
Yes,
for
okay.
number like this, B and gamma and V and G and so on, should be always a standard. Okay, so this one, it will be 1.4 velocity here. I calculated and I get it 1.4. You can make double check for me. Okay, 1.4 square 2G, which is 2.81. H pump is required equal. Other pressure is 410, sorry, 10 to the power 3, 9810. Z2 2.5. V is 2.5 square. 2 multiply 9.81. That's it. This is mainly calculation for calculator. You need to be good calculator. If you are a good calculator, you can get the H pump from this equation. After you get H pump, you can get power. What's power? Gamma Q H pump. H pump here, and the gamma is 9.81. Q is AV. How to get it? Any V, any A. So I take it by over 4 D square In this case, we should to change it from millimeter to meter. 0.15 multiply 2.5. So this what? This Q, this gamma, H pump here above, but be careful, what you obtain it here, this power by watt. So after you get watt, going to change it to horsepower by calculator, conversion calculator. Once you get watt, going to conversion to change it from watt to horsepower. If you forget this one, you change or select another choice. Okay? This clear? Any question for this problem?
Okay.
Yeah.
There is no question?
Regarding this Z, sir, in A side,
Z4?
Z, why we consider 0?
Because I put datum here. So I put the datum at A, and I measure B from the datum. This datum A, and I measure B from this datum. So here, if I put datum, so this datum is 0, and I measure the other one from this datum, which is 2.5.
Okay. Fine. And this gamma, we put 9810,
Yes.
and below we put 9.81. When we calculate power,
This 9810 here.
you put 9.81 or 9810?
9810.
Okay. Okay.
Yes.
Fine. Clear.
Okay. Answer is B.
This HP is head loss in pump, right?
This HP head of pump.
Oh, okay.
Okay, this head of pump. But this horsepower, this unit for the power. Okay.
Oh.
Here, it's just review. The power of pump is gamma Q head of pump, which is the previous problem. Also efficiency. Also, I write this efficiency before, output power by input power. Okay. Here applied for efficiencies. Efficiencies by definition, general definition, output by input. So if I require here the request here, efficiency for motor, so it is what output of the motor divided by input of the motor. But if you need the efficiency for pump, so it is output of the pump by input of the pump. Clear? Considering the unit, if unit the same or need to change anything, what. But if you need the efficiency for overall the system, so we check overall the system. So we need output, general output 648 watt by general input, which is 1200. Clear now?
Yes, sir.
Okay. So in case of this one given direct by a value and this one given by a value direct, same like the exam one, and you need overall, we're going to multiply this one with this one. If you multiply this one with this one, it's like cancel. If you check here, this will cancel with this. So what's remaining? This one and this one, which is including here. Clear? Okay. So overall efficiency in case of turbine with generator, in case of motor with pump, we're going to make a times between motor and pump and turbine and generator to get the overall efficiency for the system. Okay. Clear?
Clear.
Any question?
No, sir.
We go to next one. So I finish this slide and going to break. Before we start frictions, hydraulic grid line and energy grid line. So difference between hydraulic grid line and the energy grid line. Okay. You remember H total equal H or B, whatever H is equivalent to B. Static plus dynamic. You remember this one? Or H if you want. You remember this equation? For any
Yes.
point here, I represent for the red line by total energy, which is energy grade line. So if you remember the problem we solved it together for L shaped like this, it's measure total, correct? It's measure total for L shape. This one, for example, L shape, it's measure total, correct? And the normal one, it's measure what? Static,
Static.
correct? So
Yeah.
along this pipeline, I measure both at different location. Here, I measure total and static. Here, I measure total and static, and so on. Measure total and static, measure total and static. Okay? So why is this? It's decreased like this. We don't have anything in between. So for sure, the only reason is what?
Friction loss.
Yes,
Static.
due to losses. Due to losses. So due to
Gradient.
losses here, the energy is decreased. Okay? But I see the two line is parallel all the time. Is this logic? Yes. Why? Because the first one it measures the total, and the other one is measure static. So all the time the line, the difference in between total minus static, it is referred to
Dynamic.
Dynamic.
and this dynamic is equivalent to v square over 2g, correct?
Yeah.
Yes.
Correct.
And g is constant, so it's mainly related for this difference for velocity.
Velocity.
And velocity related direct with continuity equation. Q, this pipe, so N equal out. So this one constant, sure. So the relation here between A and V. So we don't have any change in velocity, even this one constant.
Yeah.
Only when this one change, velocity change. So if you see the diameter not a change all the time, so all the time we'll see this part of the velocity not a change. So all the time this part velocity square over 2g not a change. So the two lines difference all the time not a change. Only if diameter
Changes.
Changes.
once the diameter change, this range is going to change by increasing, decreasing according to the diameter. If diameter decrease, so velocity increase. If the
Increase.
velocity
Pressure
increase,
decrease.
this range it will be like this. If this one, for example, at this cross section is going like this, the cross section for the diameter decrease. So what happened? We'll see the two line like this, and this range is increased v square over 2g after the decreasing diameter. You understand me? But we are aware here, and we know line is called energy grid line, and we have a line is called a hydraulic grid line, and the difference between these two lines is referred to dynamic part. Referred to dynamic part. We have one question theoretically related for this one in the exam coming a lot. Okay, energy grid line and the hydraulic grid line. Difference between these two is related to velocity
Dynamic.
head.
Dynamic.
Dynamic head. Clear?
Yeah.
Okay.
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 Take a break.
Okay.
Okay, I'll give you a break, and after that we're going to continue for the part for friction and the very, very important equation in the exam. Okay, H losses. Let's take a break. 10 minutes maximum, it's okay. Okay, take a break. Recording, it's not. Now it's okay. Again, Varsi-Beibach equation, HF is equal FL over dV square over 2G. This used for pipeline. Okay, but the losses, it's coming from two ways, major and minor. Major losses, it's for pipeline. Minor losses for the fitting in this network, like any elbow, any T, any entrance, anything with pipeline, but it's not pipeline itself. So the final equation for this one, these losses, H losses total is equal the part for major losses, which is F L over dV square over 2G for pipes, and the K V square over 2G for component. This equation save, please. Same like Q, not given, almost for many times not given, sometimes given, sometimes given. Okay, we'll see some problems. I bring it in some exams, it's given, and some another it's not given. So save it, please. FL over dV square over 2G, and it's coming a lot. Coming for calculation in the part for major only. Sometimes coming for calculation for minor only. Sometimes coming to calculate both together in one equation. Okay. Sometimes H losses, it is a parameter in the equation. Just calculate it and continue calculation for the remaining terms. Okay, according to the problem. So it's coming with different shapes. Okay. Here, let's see the each variable refers to what? F friction factor. From where? In the exam, given. Why? Because the only way to get it from chart. I will describe with you the chart because we have some question theoretical coming for the chart itself, but for F itself, it's given in the exam. F. Okay. L, length of the pipe. D, diameter of the pipe. Velocity in the pipe. G is constant. V, it's not a change if the diameter not a change. So if you have network, this network vertical, horizontal, then vertical, and so on. If the diameter not a change, we can count all lengths and consider as one term. This length plus this length plus this length plus this length, and so on, all together. If diameter is the same, because the velocity not a change. If the diameter not a change, if the diameter a change, we're going to divide the calculation of the pipe. This is the meaning of the sum. Okay, we calculate L1 D1 V1 squared over 2GF plus L2 D2 V squared 2 over 2GF, and so on. Okay, but normally the diameter not a change, so L we count all lengths together and we calculate one term. For component, K V squared over 2G. V is normally given, G it is constant. V, if it is not given direct, it's given by Q, and you can get it V from the equation of the Q is equal AV. This is the regular equation used. Where is K? Same like friction factor, but this friction factor for pipe, this friction factor for component. So this coming from where? From tables. So the only way to get it in the exam, given, same like if, exactly. This coming from table. We have tables for elbows with different elbows. We have veins inside elbows. This elbow is 90, is 45, is 120. It is have number of veins. How many veins? It's tables related for tables. So the only way given. Okay. This clear? All terms clear? Okay. What is the dimension of Darcy friction factor?
Dimensionless.
Dimensionless. F is dimensionless. I don't going to solve this problem first. I will go for Moody chart. No, this no also. Let's see Moody chart first. Okay. After Moody chart, I go back to the two problems. The two problems before this, including in the exam too. So once we solve it, we solve two questions in the exam. But before, I need to continue the friction factor. Moody chart, Moody diagram. Moody diagram is the chart to get the friction factor. Let's see the parameters here. This parameter is Lerion's in the x-axis, which is referred to horizontal lines. Vertical lines. This vertical line is dotted. The dotted line vertical, you see the vertical line dotted, refer to Reynolds number. And this scale is logarithmic scale. So it's 10 power 3, 10 power 4, 5, and so on. This logarithmic scale. So this Reynolds number. So the x-axis for Reynolds number, dimensionless. Y-axis, which is referred to the horizontal lines. This y-axis refers to horizontal lines. This for friction factors, dimensionless. Okay. The last one, we have another axis. This 3 axis here. The third axis here is relative pipe roughness. Relative pipe roughness, which is epsilon by d. If you don't see this one, epsilon by d. Epsilon, it is roughness for the pipe according to the type of the pipe, we have a roughness value. From where? From tables. Same like this table. This type of the table here gives you, you search what is the type of the material according to the problem. You see, this iron, you saw the epsilon is 0.15. So we put this one search here direct for 0.15. No, going to make dimensionless ratio first. This epsilon, take it divided by the diameter you need to calculate the diameter for this pipe. So epsilon by diameter, get value. This value refer to this line. You see the curved line here, the solid line, this curved line is slightly curved here, and they have a big curvature in the below. You see these lines? Okay, solid lines, these solid lines. This refers to relative pipe roughness. So we have three things: relative pipe roughness, Reynolds, and the friction factor. These are three parameters, three all dimensionless. Okay, the range is here. This range for Reynolds number up to this, which is around 2,400, this 1,000, so this around 2,000, this 10,000 here. So between this one and this one, 2,000 and 4,000 here, this for transient. So before that is laminar, after that all is turbulent, going to turbulent. After this term is turbulent. The relation between friction factor and Reynolds number is linear in the laminar. Linear in the laminar. So we have a direct equation to calculate F in the laminar. 64 by Reynolds number. 64 by Reynolds number. And this one is linear. But for turbulent, it is all related to the all curved line. We have roughness, relative roughness calculation. We have Reynolds going to intersect between these two like this, and going left to get the friction factor. Take friction factor, put the equation for factor calculation, for friction factor for losses calculation to continue and get the equation. So we have another important notes. Yes, this line, a smooth pipe. Main engineering, once you see smooth pipe, so we don't have any friction low, zero. We don't have any friction, low in turbulent range. In turbulent range, even this smooth pipe, we have a friction factor value. But this one is the lowest value. The lower curve here. You see this curve, lower curve. Why I focus for this one? Because this is the question coming in the exam. This is a question coming in the exam. Let's see the question coming like this. Like this. No, I don't need to write it here. We can remove it after that. This one is coming like this. This A, B, C, D. And the question asks in turbulent range, which one is referred to the smooth pipe? A, B, C, D. What is the answer?
B.
B.
The answer is
B.
Exactly. This is a question coming in the exam for Moody HR. Okay. Let's go to the problem solving. Any question for Moody chart? No question?
Friction flow for laminar flow, friction factor we given the formula 64 by RE. Right?
Yeah.
But for turbulent, we have to calculate with by considering this roughness.
Yes.
But transient or transient?
Also the same. Transient is the same turbulent, but transient it's not coming normally in the exam. This range is very small. Normal equations between laminar and turbulent, and also it's mainly for turbulent. But by the way, for whatever this one or this one, it's given value. But you can remember this one, keep it in your mind here like this, 64 by Reynolds number. Maybe he play with you. Okay.
Okay.
But regular, F is coming. Same like case.
Okay.
F and the case given, no problem.
So in the formula, which is friction factor 2D, if you can go back to the chart. Yeah. 2D by rho V square T delta P. What is that delta P?
This one?
Yeah.
This one, the difference pressure.
Okay. And the T?
But this one coming from different ways to get a relation between this one and this one. Because if you're going in details to get friction factor, Reynolds is sometimes not given direct because velocity is not. Sometimes we don't know. We don't know the velocity value, so we don't have Reynolds. we're going to make something like iteration. Just adjust what is F, and after F get V, from V reuse, so get the charge, get F again to check to the difference is the same or no, not the same, take the F new, and so on, make iteration till up to the error is be minimum to just focus. Yes, this is the almost the correct answer. This is for undergrad solution, not here. As you know, the iteration problem is take time.
Yeah.
Okay. Let's read this problem. This problem, one of the problem in the exam actually. This is easy here. Water at 25 Celsius flowing through 1 kilometer. This what? Length. This length. GI, this is the type of the pipe of the material here is GI. 200 millimeter, which is diameter. Rate, which is Q. So we can write it here. L is 1 kilometer. D is 200 millimeter. Be careful for units, please. For example, this one, it will be 0.2 meter. This one, it will be 1000 meter. Q also is 0.07 meter cube per second. A value of the transverse friction factor is 0.02, which is F.
HF.
0.02. Density of the water 1000, this rho. What else? You need pumping power, kilowatt. So he needs power. Power is equal gamma U H pump. So let's start. Gamma is equal to what?
Rho G.
Gamma is
Rho G. Rho we have, G is constant. Q is given, so it's easy. G is Q, and I write it the same. H pump, we needed to calculate it from the equation, long equation, correct? So rho I have, G I have, Q I have, so the remaining is H pump, correct? Let's side calculation here and going back to substitute it in this side. So H pump, B over gamma plus Z plus V square over 2G plus H pump equal B over gamma plus Z plus V square over 2G plus H losses. So this first stage, this second stage, correct? Correct. Any information about pressure? Any information about pressure here?
No.
No. So we cancel together. Any information for elevation? No. We consider it horizontal.
Cancel.
Velocity. Any information about the diameter change?
No.
Third question for the pressure outside.
Pressure, we don't have any information here for pressure. So we consider it as the same, open, like atmospheric.
Capital.
Also Z, so horizontal. And the Q and diameter not to change, correct?
So V1 equal V2.
The velocity change?
No change.
And let same like output. So it's cancel H pump with H losses, yes? So remaining is H pump
0
is equal H losses. So the only pump required to cover the losses during the pipeline, that's it. Okay? So how to calculate losses? Here another equation, F L over D V square over 2G, correct? We have any minor losses or only major?
Yes, we have losses friction. We have 0.02.
We have only for major.
Major losses.
We don't have any minor information about elbow or something like this. So if you don't have any information for case, so early we have FL over DV square over 2G for major. Let's start F 0.02,
0.02.
L 10,000, D
10,000 cube.
0.2, 2G, V, we have Q. So from this Q, we need to get velocity. Go here with another color. Velocity is equal Q over A. Q is 0.07 pi over 4. 0.2 square. So we calculate velocity. Quickly calculation here for velocity. Let's see calculation for velocity. 0.07 by 4 divided by 0.2 divided by 0.2. 2.23. 2.23 meter per second. So here 2.3 square. Okay, let's check again. 37 by 4 divided by 2.23. So this one H pump. From this equation, calculate H pump. Go back for the here. Rho 10 to the power 3, G 9.81, Q 0.07, H pump calculated from here. That's it. Then get the answer. Easy. If you focus for the problem, what is the main calculation for the problem? Losses. The pump equal losses and the main calculation for the losses. Once you get the losses, you go substitute for the power equation and you get the answer. That's it. Clear?